In this video, we're going to explore some of the very basic principles behind acidity and pH. When we're discussing acids and bases, we often need to measure concentrations over a very large range. And so pH and pOH are systems which help us keep track of these very large ranges. When we're discussing pH and pOH, we use a log scale. If you're not familiar with a log scale works over factors of 10. And we'll see what that means for us in a little bit. In order to calculate pH, all we do is we take the negative log of the H3O plus concentration. Now note here that H3O plus and H plus are often used interchangeably. If I have something, for instance, like hydrochloric acid, remember that's a strong acid, and so what that really means is that in solution, I have H plus and I have Cl minus. The H plus ions then go on to interact with water to form what we call a hydronium ion, H3O plus. Take note then when discussing acidity, the terms H plus and H3O plus are often used interchangeably. They really mean the same species. And so I say that so that you recognize that if you see pH is equal to negative log of H plus, it's actually the same thing. And so just make sure that you recognize that H plus and H3O plus are really talking about the same species. And so to calculate pH, again, we just take the negative log of that H3O plus concentration. To calculate pOH, we take the negative log of our OH minus concentration. Now there's a very key relationship between the pH and pOH of a solution in that the sum of those solutions will always equal 14. And so let's just take a look at that simple relationship. And so again, pH plus pOH will always equal 14. Therefore, if I have an acid with a pOH of 11 and I want to know the pH of that, it's easy enough to see that the pH is going to equal 14 minus the pOH, or in this case, a pH of 3. Likewise, if I have a base with a pH of 8, and I want the pOH of that base, the pOH is going to be equal to 6. And let's say I have an acid, again, with a pOH of maybe 10, since we just did 11. If I have an acid with a pOH of 10, then the pH of that acid is going to be equal to 4. Now I mentioned previously that pH uses a log scale. What this means is that as we move in units of pH, every move of one pH unit is actually a 10-fold difference in our hydrogen ion concentration. In other words, if we have a solution with a pH of 1, it is actually 10 times more acidic than a solution with a pH of 2. A solution with a pH of 2 is 10 times more acidic than a solution with a pH of 3, and so on. And so a solution with a pH of 1 is actually 100 times more acidic than a solution with a pH of 3. pH of 1 is 1,000 times more acidic than a pH of 4, and so on. And so let's take a look at a couple of easy examples. If I want to know the pH of a solution in which the hydrogen ion concentration equals 1 times 10 to the negative 9th, then I just set up my pH equation, and I'm going to get pH is the negative log, remember, of that H plus. So our pH in this case equals our negative log of 1 times 10 to the negative 9th, which will be a pH of 9. In the second example, I'm starting with a pH of 7, but I want to know what the hydrogen ion concentration is. And so we have to utilize the properties of the log function. We know that pH is equal to the negative log of H plus. And if we look at the mathematics of log, and that it's a log base 10, what this means for us is that our H plus concentration is going to equal 10 raised to the power of the negative pH. And so, in this case, I want to know the concentration of hydrogen ions in an acid with a pH of 7, and so my H plus concentration is going to be 10 raised to the negative 7th power. Or, written in scientific notation, it will be 1 times 10 to the negative 7th molar. Most of you are probably familiar with the basics of the pH scale. The pH scale ranges from 0 to 14, with 7 being considered to be completely neutral. This means that at a pH of 7, our concentration of hydrogen ions in the solution will be equal to our concentration of hydroxide ions in that solution. As we discuss pHs that are below 7, we're starting to get a buildup of hydrogen ions in there, and so our acidity increases. And so as we get below 7, lower numbers mean that we are more acidic. As we start to get to pHs above 7, we're starting to build up more hydroxide ions as compared to our hydrogen ions, and therefore we're getting more and more basic. And so pHs below 7 represent an acidic solution, pHs above 7 represent a basic solution. Remember too, like I said, that this is a log scale. And so in other words, an orange with a pH of 3.8 is 10 times less acidic than vinegar at a pH of 2.8. Let's take a quick look at a very general acid-base reaction. A strong acid and a strong base will always react to form some sort of ionic salt and water. And so what we're looking at is an exchange reaction. We have our hydrogen of the acid coming together with our hydroxide of our base, and then the metal from our base coming together with the anion from our acid in order to form our salt and then water. Sometimes it is helpful to write water as HOH rather than H2O because it makes it a little bit easier to see that it is simply the result of an exchange reaction. And so if we consider the driving force here, we recall that water is a very weak electrolyte. And so the driving force behind this reaction is the formation of a weak electrolyte. And now we want to take a look at what the net ionic equation is for this reaction. So we have our molecular equation, hydrochloric acid aqueous plus aqueous sodium hydroxide, reacts to give us aqueous sodium chloride and liquid water. We write everything out in their respective ions. So our hydrochloric acid is a strong acid that will break up into its ions. Sodium hydroxide is a strong base. It breaks up into its ions. And then on the product side of the reaction, NaCl is aqueous, so we write that as its ions. And water, as a pure liquid, is written together. And then we take a look at our spectator ions, and we see that Na plus and Cl minus don't change from one side of the reaction to the other. And so in our net ionic equation, we can take those out. The net ionic equation of any strong acid plus any strong base will be this exact same equation. So in this video, we provided a very brief overview of acidity and pH. Those of you who go on to CHY 115 will get a much more in-depth look at acidity and some of the inner workings of it. But for now, hopefully this has been helpful as a brief introduction. If you are looking for some more information on acids and bases, please be sure to visit the website.